Start the recording, close that. Okay, cool. So the very first problem you said, which is exercise 4.2?
Yes.
Okay, cool. And that was the one where you were given some system Verilog code and you were expected to translate it into a circuitry, right?
Yes, yes.
Okay, cool. So what'd you end up getting for that?
Um, so I can't share my screen, but because I have two different computers right now, but I basically had like a um register that output um A3 to A0. And then I had some output logic,
Okay.
and that's basically what I had. And I had logic for Y1 and Y0.
So as a question for you,
Yeah.
analyzing the block of code that 4.2 is, what kind of logic is it? Is it combinational or sequential?
It's combinational
Okay, and how do you know that?
because it says always combination.
Exactly. So if that's the case, why do you have a register in your schematic? Because a register is a sequential unit.
Because I had no idea what to do.
All you don't even need the register at all. It would just be the actual output logic, the combinational logic. You wouldn't need a register.
Okay.
So let me go ahead. I am familiar with the problem because I saw it earlier, but I'm pulling it up right now just to make sure I'm looking at the right one. That would be 4.2. Yes, it is that one. It's the one where it was basically an if block, an if else if block, and it just outlined the different cases, right?
Yeah.
What did you get for your output equations?
Um. So I tried making an I made like a little input and output table, and my equations don't really make sense. I had one for Y1 and one for Y0,
Okay.
and then my Y1 was A naught B naught, or A naught B, and then I simplified that to just A naught.
Okay. You put A, but A is a multi-bit signal. So
Yeah,
which bit?
I was just I was just trying to get like
So I'll go
yeah.
ahead and actually kind of go through 4.2. So everyone who's joined in, we're going over problem 4.2 from the text, which is your first homework problem that's due today. So I'll go over that one. Um, but essentially, all it's saying is it's an always com block, and it goes through a bunch of different cases. So the first case says if bit 0 is on, then the output of y is going to be 1, 1. So in other words, y bit 1 is going to be on and y bit 0 is going to be on. And essentially the way you want to do this is you're going to want to make a truth table. That's probably the easiest way to do it. And then from there you can do like a k-map and stuff. So what I'll do is I'll go ahead and write down the other ones. And I'll just do it like this. Next one is 1, 0. Next one is 1. Zero, zero. It is. So this is basically what the code is spelling out. So if the bottommost bit 0 is on, then we output 1, 1. If that's off, but the next one's on, then we output 1, 0. If both the bottom two are off, but then the third one's on, then we output 0, 1. And then if all of them are off except the top bit, then we output 0, 0. And if none of those are true, then we output the bottom 2 bits of A. So I'm going to go ahead and put this in a truth table really quickly. Let's see. Okay. Now I'm going to turn this logic into a truth table, And I'm going to do it a little bit differently than what you might initially think to do, because what someone might initially think to do is to do every possible case, which would be 16 rows, because we have 4 different inputs. So 2 to the 4 is 16, so we'd have 16 rows in our truth table. But there's a way to do this using don't cares, such that we have many less rows. So what I'm going to do is the following. I'm going to think about what this line of code means. And what it means to me is if the bottommost bit is on, irregardless of what any of the other bits are, if the bottom bit is on, then we always output 1, 1. And so what you can write in a truth table for that would be the following. If a bit 0 is 1, if it's on, then what we can do is we can say, well, I don't care what bit 3, bit 2, and bit 1 are. It doesn't matter what they are. If this bottom bit is on, then the output's going to be 1, 1. And you can do a process like this for the rest. So the next one is else if. So otherwise, which is to say the bottom bit is not on, but the next bit is on, well, then I output 1, 0. And again, in this case, all I said was if A was not on, but A0 is not on, but A1 is, then I don't care what the other bits are, I'm going to output 1, 0 regardless. And so those don't cares. And this kind of progresses just like that. So again, in the next case, we do both of those are off, but then the top one is on, irregardless of what this bit is. And then finally, this corresponds to that row there, which is the top bit is on and the rest are all off. And for that, I'm going to write these outputs. So for that third one, I have 0, 1. For that bottom one, 0, 0. And there's one more line in this truth table that I haven't written. So I've gone through the case of the if, this else if, the second one, and this second one. What would I do for this last guy, for the else? It's a bit of a harder one. What would I do? Anyone can answer.
Are you just asserting what A is at the time?
Exactly, yeah. So what would be my inputs to correspond to that last row?
Would it just be A1, A0, and Y?
So like, what would A3 be? What would A2 be? What would A1 be? What would A0 be? Because we've covered. I'll tell you that we've covered 15 out of the 16 possible cases using these statements up here. But there's one that I'm missing, and what's that case that I'm missing?
Everything 0?
Exactly, yes. So all zeros is the last case I'm missing. This top one here accounts for 8 of my cases. This next one accounts for 4, 2, and 1. It's almost 15. And then this is my 16th case here. Now, in this case, what do I put here? What would be my output?
Would it just be A1 and then A0?
Yeah, but what is A1 in that case? And what is A0 in that case?
Is it just 0? No. Oh.
So you can think of it two ways. You can either say, well, it's going to be A1 is 0, or because we're in this very specific case, we know that A1 is 0 and A0 is 0. So we can just write 0, 0. Okay, so any questions with how I turned this set of code into the truth table?
Can you ever have it where, like, your system just messes up and you get, like, all ones for your A's, and then you output A1, A0? Like, is that ever a possibility that your code just, like, goes crazy?
Well, if you have all ones, that would fall under the branch of this guy. Because the least significant bit is 1,
yes.
and then I don't care what those other ones are.
Okay, I see. So this really does cover every single case.
Yeah.
Got it.
The only case it doesn't cover is if you don't receive logical inputs. If you receive, like, because we expect 0 to be 0 volts and 1 to be, say, 5 volts. If you get, I don't know, negative 2 volts or something, or you get 2.5 volts or something, then that wouldn't account for that. But in terms of logical signals, yes, it accounts for all the cases. So we've written a truth table, and now the question becomes kind of independent of the Verilog code, we have a truth table, and now you write the output equations given that truth table. Would you guys like me to go through writing the output equations, or would you prefer that I work on a different problem?
So for this problem, I was really curious how we did, like, I was fine with the equations and output logic, and that's fine if anybody else wants to go through it. I'm totally cool with that. But my question around this was like, how are we getting the one, like, were we having two separate outputs, one for y1
Yep.
and one for
Yep.
y0? Oh,
Two
okay.
separate outputs,
Okay.
so two different output equations. Yep.
Okay, so those were two separate like little output blocks in our
Yep.
schematic.
Exactly.
Okay, that was my big question. But yeah, if Leb or Good Noodle wants to go through it, I'm fine too.
Yeah. Would you guys like me to go through it? Yay or nay?
I,
You can go
You
first.
go. No, you go. You 100% go first.
All right, yeah, I'll go through it. So there are a few ways. I can either do circle my rows where I get ones and then write the output equations, or what's the other thing I can do?
K-map.
K-map. I'm gonna do K-map for. I'll do K-map for y0, and then I'll see how I'm feeling if I want to do the equation or the K-map for y1. So we'll start with y0. Okay, cool. So I'm gonna go ahead and start by drawing out my K-map. And what are my dimensions of the K-map gonna be? Kind of hinted a little bit at it since I drew it in square, but what are my dimensions going to be?
It goes up to 16, right? Because there's 4 bits.
Yeah. Yep.
Okay.
So it's going to be a 4x4 square here. There's 4 bits, so I'm going to have 2 bits for the column and 2 bits for the row. So I'll go ahead and do A3 and A2 up here and A1, A0 down here. I'll go ahead and label my rows and columns. And remember that when you label these rows and columns, that you always have to use a gray code for every consecutive sequence, which just means you only change 1 bit at a time. 1, 1, 1, 0. And the next thing we're going to do is we're going to take a look at this truth table and fill up this entire K-map with it. So I'll do the easy one. I'll do this bottom one, which says that when you have 0, 0, 0, 0, you output both zeros. So that would be this case here, and y1 in that case is 0. And I'll even give you guys a treat. I'll do this one too, another easy one, which is exactly the same except a bit 3 is on. So that would correspond to this guy here, and that's off. Now, how do I do the rest of these? Say, for example, this top row. Y1's on here, but how would I figure out my position if I have a bunch of don't cares?
Are we doing Y1 or Y0 right now?
Y1.
Y1? Oh, okay.
When we're dealing with don't cares in K maps, we can, because it's saying that it can be on at either of them. We just put a 1.
Yeah, but where? So, like,
Oh,
for
okay.
example, according to this row, Y1's supposed to be on, but what does this correspond to? Where in my K-map do I put a 1?
So a bit has to be a bit. That says a bit 0, right? So a bit 0 has to be 1, and then all of them, and then up to then, we just put a 1 and zeros, or up to a bit 3, I guess. There'll be
let's
1.
Let's take a look at this one. All we're saying is that if a bit 0, if the bottom bit is on, it's going to have a 1 in that box. So a bit 0 is 1, and a bit 0 is 1. So in this column, this corresponds to every position where a bit 0 is on, and so does this column. A bit 0 is on. So in every single one of these, we say that y1 should be on. So we put 1 in every single box. Because in all of these boxes, a0 is 1, and all of these boxes, a0 is 1. So any questions about that? And like I mentioned before, When I said earlier that I had 8 possibilities accounted for by this first row, you'll notice that I have 8 possibilities accounted for when I put it in the key map too. So the next one is going to be, so we are done with this one. I'll go ahead and do this one next. Where would I look in my key map for this guy? And if you want to say, like, it's this row or that 2x2 box, you can say that too. But where would I find this guy in my key map?
So I think that would have to be rows 3 and 4, because that's A1 equals 1.
Well, not only is it A1 equals 1, but it's also A0 equals 0, right?
Oh, yeah. So that would have to be row 3 then. Or row 4, row 4, row 4.
Yes. No worries. Yeah.
This is so confusing to me for some reason.
It can be a little bit confusing. You can do the whole 16-line truth table. You can totally do that and do it one by one. But I wanted to show you guys a different way so that you can save on writing and your hand won't cramp during tests.
Yeah, this is actually really helpful. Thank you for going through it.
Yeah. So now I say, okay, well, all the cases where I have A bit 1 is on and A bit 0 is off, well, that's this entire row. So I fill it all up with 1s. And then my last case, I have 0s, but that's just the remainder of the spots that I haven't filled up. But I could look at it and say, well, if A bit 2 is on and these two are both off. So A1 and A0 are off is this row. And then we know that A bit 2 is 1. That would correspond to the second and the third column, which are the ones I just filled with 0s. And so now I have my K-map for it. I have 0s in the first row and 1s everywhere else. So how am I going to circle this stuff? What am I going to do?
Wait, can I ask a really quick question?
Yes.
So why wouldn't our row with A3 equals 1 and everything equals 0, why wouldn't... Oh, we're doing Y1. Okay, I got it. Never mind.
No worries. Okay, so how would I circle my 1s here to make my equations? What would I do?
I think to get the smallest amount, we would circle 2 rows and then just 1 row by itself.
So,
Two.
like, for example, like that? Around the 2 middle rows?
Yeah, and then circle the bottom row.
Okay, so I agree with that first part, and you could totally circle just the bottom row by itself, but remember that even if there's overlapping, we want to circle as big of regions as possible. So what do you think we should do with that in mind?
So circle the bottom row with the third row.
Exactly.
2.
Yep. As mentioned, even though if you just circle the middle 2 and then just circle the bottom row by itself, that's correct. It's not the minimized gate form, though, because you still have like 1 extra gate that you could have minimized out. Here, though, it's fully minimized SOP form. And then we can write the equations. So I'll ask you guys again, that middle box that I drew around row 2 and row 3, what equation corresponds to that? Or what term corresponds to that? What do you think? What would I write for the term of that big box in the middle?
A0?
Yeah, you would write A0 because in these 2 rows, A0 is the same and A0 is 1. So I would write A0. And what about for that bottom box? What would I write?
That's A1.
Exactly. And let's just check the truth table and see if this makes sense to us. If A0 is on, Y1 is on. Or if A1 is on, Y1 is on. But in every other case, it's off. So this kind of intuitively makes sense if we compare the equation we got to the truth table. And so I can draw the circuit for this as well, which would just be a single OR gate. And we could also do the same for the second one, Y0. Okay. Would you guys like me to go through the one for Y0 as well? Or do you want me to work on another problem?
I'm good on this one if you guys are.
I'm good too.
I'm good too.
Yeah, so the last step would be key map, or you could do it straight from the truth table, draw out the schematic, and I'm pretty sure they only wanted you to draw the schematic, right? That was the only thing they asked for?
Yes, that's right.
Okay, cool. Are you guys alright if I erase this from the board?
Yes.
Yeah, I'm fine.
Yes.
Cool. Alright, as for the next problem, what do you guys want me to go over next?
I vote for the last problem in the set, which was like the parameterized ones, because I think we've only done like parameters for the FSMs like once or twice in TA hours, and
Yes.
I could definitely use a refresher on that.
Okay. Yeah, we can talk about that. Yeah, let's do that. I'll go ahead and share my screen with everyone so that I can actually type, and so that everyone can see it. Okay. So, correct me if I'm wrong, but this problem asks you guys to implement an 8-to-1 mux, but with but a parameterized 8-to-1 mux? No, that's wrong. No, that's something in 4.8. This one's the register. So it's a parameterized register, right?
Yes.
Okay. So parameterized, and it's synchronously resettable. Clock reset.
And it's like
key.
the n bit part was with the widths for n bit.
Okay, so I'm gonna zoom in here. Close that. New file. 10-2-3. Okay, while I'm doing this, how did you guys feel about the exam on last week? How was it? Painful, unfair, reasonable?
I feel like I didn't have enough time for me. Like I ran out of time, so whenever she was like 10 minutes left, I just went through as many problems as I can and just wrote down like base stuff or whatever, so I can try to get as much points as possible.
Right. Okay, let's see. Put that on this. Okay, you guys should be able to see my screen now, can you?
Yes.
Okay, cool. So let's go ahead and start this. And I'm going to start. So this asks you to make a synchronously resettable register. I'm going to do it a little bit differently. I'm going to do a different example. I'm going to do a asynchronously settable register. And I'm going to do it non-parameterized first so we can kind of get an idea for how to do it. And then we can move into the parameterization. So remember that whenever you do any Verilog or system Verilog module, you always start with the keyword module. And that's going to be followed by the name of the module, which in this case they ask you to name it regnr. Let's see, reg. And then I'm going to call it ns, only because it's going to be settable, not resettable. And then the next thing after that is my port list. And I'll put stuff in the port list in just a second. Now, as a question to you guys, what goes in this port list? What would I put in here?
Input logic and output logic, right?
Yeah, exactly. My inputs and my outputs. So thinking back to the problem, what are my inputs and what are my outputs?
We have inputs clock, reset, and D. And then the output... Oh, sorry. The output is that a Q dot D?
It's Q and then a period, so it's the end of a sentence.
Oh, okay.
So it's just saying D is an input and then Q is another output, yeah.
Oh, okay, thank you.
So logic, and then D is our input, D, and I'm going to go ahead and make some space here. 0, 0. So I'm filling that in with a 0, 0 now because I'm going to be changing it in a minute. Just remember that whenever I put 0, 0, that's the same thing as saying a single bit thing, as saying a single bit value. So clock and set here are 1-bit values, and so is D, and so is Q. Output here. And again, if I just left it like that, it would be the same. Okay, so like I said, I'm changing it, so I'm doing it settable, asynchronously settable. And I'm going to put that 0, 0 here, only because we're going to be using that in a minute to make this parameterized. But for the moment, let's not worry about parameterizing it. Let's just get the general functionality done. And the general functionality starts with, we make a flip-flop or a register. So how do we make a flip-flop? And I can actually zoom in a little more.
You have to say always FF and then at the pos edge.
Yes, pos edge of...
Clock, CLK.
Exactly. Now remember that this is an always block, and this is called the sensitivity list. So what that means is every time this action occurs, or this event occurs, we're going to read inside of the always block and evaluate it. So here what this is saying is that at every positive edge of the clock, we reevaluate what the internals of our register are going to be reading. So that's why it instantiates a positively clock triggered or positive clock edge triggered flip-flop. We can, if we wanted to, put a begin and an end, but as I might have discussed before in previous office hours, it doesn't matter if you have a single statement underneath always block, you don't have to put begin end. Okay, so now what am I going to put inside here? And remember that I'm not doing quite the homework, I'm doing a settable one instead of a resettable. So what would I put in here? What do you think I should put inside the always block? And it's okay to be wrong, guys. Don't worry about it.
If reset Q gets 0 or something.
Yeah, that would be what you write if this was a resettable flip-flop, which in your homework it is. But in this particular example, I'm doing a settable one. So if it was reset, Q would get 0. But if it's set, then what does Q get? Instead of 0. What would I put
1.
for Q? Yeah, 1, because it's a set. So I can write that as just 1, or I can write that as 1 bit of binary, 1. Either way works.
Wait, I thought it was resettable.
Yeah. So the homework problem is a resettable register. I'm doing an example as a settable. Yep.
Oh, okay, I see.
Yes. So if set, Q gets 1, and you can also write it as 1 bit of binary 1. Like this. But I'm just going to write it as 1. And what happens otherwise? So else, what should I put? What does Q get in the case where set is not on?
D.
Q gets D. It just behaves like a regular flip-flop, exactly. Now again, like I mentioned, you don't need the begin and the end here because if-else counts as a single complex statement, so it can be ignored. So I'll actually do that. I'll get rid of the begin and the end. Okay, so is everyone all right? Yeah, go ahead.
Yeah, what would, because when I do this in like Visual Studio, it just populates the begin and end. Like what would a block that requires begin and end look like in here, just out of curiosity?
Yeah, I can do an example. So maybe something like, just ignore this stuff. If we had, let me put begin end, 2 separate lines. So maybe this is actually 2 registers that we're doing in a single FF block because they're both registers that work with the same pos edge of the clock. Q gets D and A gets B, for example. these would count as two different statements, and so you need a begin end for that. But again, the way that I've written this is like doing two registers, one with the input Q and the output, one with its input being Q and the output being called, or the input being D and the output being called Q, and this one with the input being called B and the output being called A. So this would be an example where you could use a begin end. And if you had, multiple if statements, that would be an example. So not if, else, if, else, if, else, but you have if something, and then a whole block, and then if another something, and then another whole block. That would count as multiple lines. So that would be an example, and there are many other cases. But just in general, if you're unsure, just put a begin end, just so that you're kind of guaranteed to have that entire set of code within the block, if you're not sure. Okay, so are we all comfortable with the way I've written this module, and we're good to move on to parameterization? So I'll go ahead and parameterize this module. Recall that parameterization is going to occur right over here. So we have $, and then we're going to put in stuff in this block. So this block, that's the parameter block, and we're going to put all the parameters we care about. So here, we say that we want to parameterize it to be an n-bit register instead of a 1-bit register. So if I was to look at a schematic of that, it would be something like, I'm going to go ahead and draw it up on the board. Like that. So originally we had So this was the original diagram we had. We had a 1-bit input, 1-bit output. But for this, that's what they're asking us to do, to make the input n bits and the output n bits. Okay. So now, let's go ahead and head over to this parameterization. So I'll go ahead and close my camera up. And I'm going to go ahead and write in what my parameter is going to be. So here I have to say, okay, I need to parameterize the bit width, and I'm going to call it n. So I'll use n, and you don't have to put parameter, so parameter n, and you could, if you want to, put a default parameter so that when you instantiate this module later, typically if you instantiate a parameterized module, you have to specify what you want the parameters as, unless there's a default value, and if you don't fill it in and there's a default value, it takes on that default value. So I could, if I wanted to not have a default value, omit this equals 1, but I'm going to go ahead and leave it in there. Okay. Now, the next thing is I need to actually put n into my code, and so where it's going to go is in the bit widths of D and Q. So that's why I left this as 0:0 earlier, because I knew I was going to say n:0, but not n-1. Can someone tell me why I would put n-1 instead of n? Why wouldn't I just put n?
Because our bits start with 0, so if it's 3 bits, you're only going to go 2:0.
Yeah, so if we need 3 bits, we say 2:0. If we need 7 bits, we say 6:0. We always do one less than whatever the bit width number is we want. If we want n bits, we say 1 less than n-1. Exactly. Okay, so here's my bit width for D, and here's my bit width for Q. And here's where the magic happens. Nothing inside of this code actually changes. The reason why is because if I put Q here and I say Q gets 1, it understands, the code understands that it's going to take a 1 in the least significant bit, and then it's going to fill the rest with zeros. Now, if that's what we want, great. What if we didn't want that? What if we wanted to fill everything with 1s? Every single bit with 1s? Does anyone know the syntax for that?
Can you put like the ampersand? Does that work for this case? Like ampersand?
I don't think the ampersand's going to work here. One way to do it, one way to say all the bits of Q have to be filled up, is like this. So what this says is that we have, and you'll notice I didn't put like a 1 here or a 2 here or even an n here. Note this does not work. It's not going to work if you just put n like this. Filling it in like this makes it so that it fills the entirety of Q, all the bits of Q, with what you got here, which is the binary bit of 1. So what this is going to do is it's going to say, okay, I have 1, and I'm going to fill 1 into every single bit of Q. And that's what it does. You could, if you wanted to reset it, fill it all with zeros, and it'd be like this. But if it's settable, I'd have to do it like that. Okay. That is the only change I have to make to my code. And just so you guys know, for the resettable register, you could actually just leave it as 0, because it's going to fill everything with 0 regardless of if you put this or if you put that. But if you put 1, this is going to make the bottom bit 1, so it's going to make the whole thing just 1. So everything is zeros except for the bottom bit. Whereas if you put this, it's going to load the number 1 into every bit of Q. So that is a little bit of a distinction. Okay. Any questions about the parameterization we did?
So just a quick question. If we wanted like Q0 to be 1 and then Q1 to be 0 and Q2 to be 1 or whatever, we could like say if set and then like write all of those in brackets.
Yeah. Yeah.
Is that possible? Okay.
Yeah, you could definitely do that. Don't quote me on this, but I think if you do... Is that right? That might not be correct. Yes, you could definitely do a concatenation and say, okay, this one is going to get 1 bit of binary 1, and this one's going to get 1 bit of binary 0, and then write out as many terms as you have. But that would require that you have a fixed n value here, so it's not parameterized. It's just a fixed value, so say 10, and you would have to hand write it out. There is a way to do it so it's like 0, 1, 0, 1, 0, 1, 0, 1 copied a bunch of times. I would have to check how the syntax works on it, but if I recall correctly, it's going to work something like this. So you'd say 2 bits of binary 0, 1, and then you would have to put this in the concatenation operator again. And if I recall correctly, you have to put something like this. N over 2. So you want to repeat this sequence n over 2 times. So you fill it up with n over 2 copies of this. I'm pretty sure that syntax is incorrect. I think there's a different way to write it, but it's something like this. However, you're not really going to be using anything like that in lecture or in your codes. So for now, we're just worried about a bit of binary 1. But yes, you absolutely could write each of them out individually. All right, any other questions? How would I make this asynchronously settable? What would I change this code to make it asynchronous instead of synchronous?
Next to the pause edge clock, you would put wait, are we doing for set or reset?
Well, in my code, I would put set. Yep.
Yeah, we would put set right there. So, or pause edge.
Yep. Yeah, so when we get a positive set, when we see that setting rises, we're going to say, okay, well, set is just rows, we're going to set our register. And so that's asynchronous, independent of the clock, because again, we say this sensitivity list, this always FF block, evaluates the code inside of it whenever any one condition or multiple conditions occur within this sensitivity list. So you could have positive clock happen, and then you evaluate. Or you could have the positive set happen, and then you evaluate. Or even both at the same time. As long as at least one of them occurs, then you're going to evaluate the stuff in this block. Okay. Yeah, so the only changes you would do to make this for reset is change this to reset, change this to reset, change this to reset, and have it go to 0 instead of 1. And then it asked for synchronous, so you wouldn't have this here. And I think that would be about it. So let me just check the question to make sure they didn't ask for anything else. and bit signals. Okay, yeah, that looks right. And written in the assignment, it also lists a few reference modules for how to parameterize, as well as how to make a synchronously resettable flip-flop. So if you were to do this from scratch, you would take the synchronously resettable flip-flop and then parameterize it the same way that the mux is parameterized in the code that she has posted on Canvas. Okay, cool. Yeah, so any questions about the way that we went about this?
Yes, sorry. One more time. So if we had the pause edge set, that would be an asynchronous settable flip-flop?
Yes, that's right.
Okay, thank you.
Yep. Okay, any other questions? Okay. So let's see, that was 1, 3. 4 is just your guys' resume. I mean, if you want, I can look at resumes, but I imagine everyone has questions about actual content of the course. So do you guys have any other questions you want me to go over, or conceptual things you have questions on?
Personally, I'm good. Thank you.
Yeah, you're very welcome. Any other questions for me? Okay, well, I'm still going to be here for the next 23 minutes. If you guys want, I can just, look at the next things you're going to be covering and talk about them, or I can do more example problems, or we can sit here in silence and I can talk to myself. I mean, I could really do anything here.
So, I wasn't in class today, but why are we covering resumes?
Oh, great question. The career fair is coming up in October something, I think 12th, something like that. So, sorry, what'd you say?
Oh, no, go ahead.
Yeah, so you have to submit your resume, just get just submit it, and I don't recall if Dr. Harris is going to do it this semester, but for some previous semesters, she's handed out some extra credit for anyone who's attended the career fair and taken a picture of them of themselves at the career fair. So I'd recommend going. It's just generally speaking, it's a good place to kind of get a feel for companies around the area that would be hiring not only for jobs but also for internships, which is pretty important too. And who knows, maybe you'll land an internship, or maybe even you'll meet some people you can get a job later after you graduate.
Okay, yeah, sounds good. So I had been doing a bunch of physics homework and physics preparation because I have a midterm coming up here soon.
Yep.
So I didn't get a chance to really look over much of the homework, but I had a question about late work. She doesn't accept late work, or how much does she penalize for late work?
As far as I'm aware, she doesn't accept late work. I imagine that if you submitted at 12:01, no one's gonna care. But
Right.
generally speaking, she doesn't normally accept late work.
Okay, yeah, that makes sense. Yeah. I'll go ahead and try and finish up as much as I can about this.
Okay,
Thank you very much.
you're very welcome. Any other questions for me?
I'm good if we just want to go through more examples. I don't know what everybody else is struggling with, but I feel like Verilog is my weakness.
I mean, yeah, we can talk about more Verilog examples. I can just look at problems from the textbook and use those. Are there any other requests that you guys want to go over?
I'm good with that.
Okay. So checking test bench. Have you guys gone over test benches yet?
We just went over them in the last lab, or maybe 2 labs ago, but we haven't written any test benches yet. They've all come with the labs.
Okay. Would you guys like me to go over kind of ground up how to make a test bench?
Oh my god, yes. Absolutely.
Okay. I'll do that. Before I write it, I just want to make a few notes. So a test bench is a non-synthesizable piece of code, which is to say you can't make hardware that runs a test bench. That's not how it works. It's purely for simulation. So just keep that in mind, and a lot of the things I'm going to be writing are for simulation only. They will not be able to be made in hardware, so that's very important. Okay, so I'm going to go ahead and write my module. I'm going to call it test bench. To be original, I'll call it test bench 4, because why not? And typically in test benches, you don't have anything in the port list. Instead, you write all of your signals as internal logic signals. And so you would say something like logic. And we would take whatever our module is. Let's say, for example, it's the regns module. So we say, okay, what are my inputs and outputs of this guy? So I'm going to go ahead and make a comment here. This is going to be my DUT signals. Anyone know what DUT stands for?
I'll be honest, I have no idea.
No worries. It stands for device under test. So that's going to be the module that this test bench is actually testing. Logic. And I'll do this with... I'll do it with 4-bit inputs to be different. 3:0, and I'll say D and Q. Okay. And so now here we can kind of analyze what I've written. I have my device under test signals, and that's just the inputs and outputs of my module that I'm testing. So here, I'm going to instantiate my device under test. And all I'm going to say is I'm going to say the name of my module, which is regns. Regns. And here, optionally, well, actually, I'll finish writing it. And then I would put the name of this particular instantiation. I'll just call it DUT because it's the device under test. And I'll go ahead and put the signals in here. So the DUT, or rather regns, starts with clock, and then set, then D, then Q. So I'll put them in that order. Clock, set, D, and then Q. Okay. Has anyone noticed something that I've omitted from this code so far? Again, it's
Does that have to do with the end modules or
Does it have to do with the what?
the end modules?
What do you mean, the AND modules?
The end modules. How you have two different end modules?
Oh, no, good question. So you can actually write multiple modules in the same file, in the same .sv file, and it's fine if you have that. So
Oh, okay.
this knows that the module is the span that I've highlighted, and this knows that the module is within the span that I've highlighted here. So that's not quite the issue.
Mm.
So
And it just knows the input versus the output, or like the bit width. Wait, why did we change from N to 3? Was that just a example?
Yeah, so here's the thing. We're doing a test bench. So we need to have an actual number of bits if we're trying to test the functionality of this. We're trying to test a specific instantiation of the hardware. And so I, as an example, said we're going to have a 4-bit input and a 4-bit output. So I said D is 3 to 0 and Q is 3 to 0. When I do that, I'm putting a 4-bit input and a 4-bit output here, and my module needs to understand that this is a 4-bit input D and a 4-bit output Q. So the way that you instantiate a parameterized module and use those parameterizations is you put something like this. So here, this is saying I'm going to look at my parameter list, and the first thing that I see in my parameter list is going to be 4. So here, it's saying n equals 4. So it's going to override this default parameter, which would be 1 normally, but after I put this pound sign followed by a 4, it's going to make n 4. And so that would mean that n minus 1 is 3, so we get D is 3:0 and Q is 3:0, exactly as how I have written here in my test bench. So any questions on that?
So this is just to test our module at a different bit state than what we were originally having it at?
Yeah, because originally it was Well, originally it was just whatever n was. I put as default it's 1, but it could be anything.
Mhm.
So
Okay.
we're just testing a specific implementation where n is 4. We could, if we wanted to, make another test bench where n is 8, or make another test bench where n is 1, and then test them separately. That all works too.
Okay, but you still have to make the logistic statement of the what's it called, of how many bits are in there. Like for example, how you specified that there's a logic of 4 bits D, and Q. If we were to go up to a different number, we would have to state that as well, right?
So if you put 7 here, yeah, this would have to be 8. Yep.
Okay.
Another way you can kind of get around that is you can make another parameter, say, I mean, you could do it like this, parameter n equals 8. And then you could say this is n minus 1, and then you could put n here, just so that instead of having to change it in multiple spots, you could just change it here. You could totally do that. And so now we're testing the version where it's 7 bits, and now we're testing the version where it's 1 bit, etc.
Oh, okay.
So that would totally work, and what not? Why not? I'll just do it. So n is 4, and I misspelled parameter.
Just a quick question.
Yep.
What would happen if we were to pass in 0?
Excellent
'Cause
question. Yeah, so what's 0 minus 1?
Just
Negative
-1.
Yeah, and so it sees -1:0, and it says, okay, your bit width is negative. I'm not going to compile. That's what's going to happen.
Okay, thank you.
Yep. Let's see. Okay, cool. So we've instantiated our device under test, or we've instantiated our device under test with the device under test signals. We have a parameter here just to specify the bit width of this particular test we're doing. And so now we're going to work on the stuff that's really part of the test bench. So we have our module placed down on our breadboard or whatever, and now we need to basically feed it inputs and read the outputs. So here's what I'm gonna do. I'm gonna start by doing some of those inputs. So I'll do the following: always, and I'm just gonna do always, begin, end. So this is an always block, and you can think of it kind of like a while loop that always happens. So it just always occurs. And what I'm going to do is, or sorry, I said always occurs, keeps looping forever. And so what I'm going to do is I'm going to say, okay, I'm going to start with clock at 0, and then I'm going to delay in my simulation for 5 units of time. And then I'll set the clock to high and delay another 5 units of time. And so in your simulation and model sim, this would be like 5 picoseconds, and this would be 5 picoseconds. So what I've done is I've created a clock with a period of 10 picoseconds. Now, I say picoseconds, that's just what it's called in the simulation. That's irregardless, that's independent of what that actual circuit would be able to reach in real hardware. That's just for simulation. So if I wanted to, I could put 5,000, and I could put 5,000 here. And the only thing that would cause is for your simulation to run longer, for your simulation to run longer in order for your clock to do as many iterations. That's all it would do.
So the pound signs act as our clock gauges, or like our clock runtime?
Yeah, so the pound sign is a delay in this case. So what I'm saying here is I'm going to start my test bench, and at the very beginning, clock is set to 0. And then I'm going to delay for 5 seconds. So on my waveform, I'm going to see clock at 0 for 5 picoseconds, or for 5 units.
Right.
So it looked like this. And now, after 5 picoseconds of delay have occurred, I'm going to read the next line. Clock equals 1. And so now what's going to happen is, this is going to go up to 1, and we're going to wait for another 5 picoseconds. And then we're going to return back to the beginning and say, oh, clock is 0, because this is an always block, so it keeps looping forever.
Oh, gotcha, okay.
And so it's going to continue doing that. And you'll notice I've written this all on one line. You don't have to. You could write it on separate lines. I just do that because I want to save space to make the code not quite as long. But it doesn't matter which way you write it. Okay, so any questions about that always block?
So it's just like a repeating pattern, right?
Exactly. Yep.
Okay.
All right. The next thing I'm going to do is I'm going to put my system into a known state. So typically we'd say reset the system. Here I don't have a reset signal, I have a set signal, so I'm going to set the system. So it's in some startup state before anything occurs. So I'll go ahead and do that here. So whenever you want a condition to occur at the very beginning of your simulation, you do that with an initial block. So something like this, you'd say initial, and then you'd say begin end. So this one doesn't loop like the always block, but rather what it does is it occurs once at the beginning of the program and then doesn't occur again. So it's just a single shot at the very beginning. So what I'm going to say here is I'm going to do, say, set equal 1, and then I'll delay for some amount of time. I'll delay for, say, 12 simulation cycles, and then I'll put set equal to 0. And so what that's going to do is it's going to do the following. This is clock, set. So in my simulation, the waveforms are going to look like this, where set starts high and then goes low. Again, the reason why we do this is so that we can have the signal at some sort of known state. And I guess I'll just change it. I'm going to do reset. Typically, you do this with reset signals. And we do this so that the system's at some known state we can start from and predict how it's going to evolve from there. So we reset the flip-flop, it's all set to zeros, and then after that, we have another positive edge of the clock, and then it begins actually proceeding as we expect a flip-flop to go. Okay, so I think I'll actually do that for all of these. I'm going to pretend we did the homework problem and did a resettable register, and I'll just call these signals reset. Okay. Another thing I'm going to do here is I'm going to go ahead and decide on how I want to implement reading in my inputs to the device under test. Because what I need to do for a test bench, for it to be a useful test bench, is to have it be self-populating and self-checking. So when I say self-populating, that means it's feeding in inputs into the device under test without me having to do anything. It just does it automatically. And when I say self-checking, that means every time I input something, I'm going to read the output and check to see if that's what I thought it would be, if that makes sense, if that's a reasonable output. And in order for any test bench to be useful, you need to be able to do those two things. So it's kind of automated in a sense. You can do a test bench that isn't automated, but if you want an automated test bench, but if you want something that is much more easily usable, you want an automated test bench. And so we're going to do that with a few things. So the first thing we're going to do is we're going to figure out what our inputs are going to be. And typically, you read in inputs from a test vector file. So a test vector file looks like this. Let me go ahead and open up a new file. Let's see. File. Okay, so test vector, I'm going to write a comment here, typically has a few things. It has all of your inputs that you're testing for a specific time, and then the expected outputs when you put those through. And so what I'm going to write in here is the following. My inputs are going to be D, and my outputs are going to be Q. The reason why I haven't included a clock and reset in my inputs, and I'm not going to include them in my test vector list, is because I already have clock controlled by this block, and I already have reset controlled by that block. So I don't need to put it in my test vector file. So what I'm going to do here is I'm going to put a little comment at the beginning of the file, and when we read in this file, the comment will be ignored. I'm just going to do this for my own sanity. So I have Q, which is a 3-bit value, or rather, I'm going to put my inputs first. I'll put D first. So D is my input, and then I'm going to put Q as my output. And I'm going to call this Q expected because it should be what my expected value of Q is, rather than the one that the module actually produces. This is what I think it should produce. And so that's just notation there written to help me remember what I'm writing. So each of these is 4 bits. So here's what I'm going to do. I'm going to input 0, 0, 0, 0. And what that's going to be is it's going to be the value of D. And then I have to ask myself, okay, what do I expect Q to output? All right, well, I've just input D, and, well, let's do it like this, actually. And so what we're going to say is, okay, well, on this clock edge, D was 0, 0, 0, 0, so Q is going to be some value. Remember, initially, Q was all 1s, because is all 0s, because it reset. And after this, it's going to read in the value of D, which was all 0s. And I'll actually go ahead and change it to 0, 0, 0, 1. Just so we can see that it actually changed at that clock edge. And so what I'm going to do is I'm going to write exactly that in my test vector file. I'm going to say, okay, if I put in 0, 0, 1, I expect my output to be 0, 0, 0, 1, because I just read that into the register, so the output of the register should be the same thing. And so then you would populate this with rows like exactly how I've written, with your inputs and the expected outputs, and then a new line for every input that you're reading in from the test vector file. Okay, so is everyone fine with the way I formatted this?
How do you know, though, maybe this is later, like, wouldn't Q expected be 0, though, if your reset was on? Like, how
Exactly, yeah.
are we,
No, that's a
are
good
we going to
point.
code that into the,
We're going to
yeah.
code it up. We're going to say
okay.
we need to check it at a specific time. And in my head, I know when we're checking, so I know it's going to be 0, 0, 0, 1. But I haven't told you guys yet, so you would probably code that up first before you write the test vector file. But yeah, it just depends when we check it. If we checked it, say, at this positive edge of the clock, yeah, totally, Q would be 0. But if we didn't start checking until after reset was off, then we would actually see that new value as the first thing, depending on when we check it. All right, good question. All right, so the next thing I'm going to do is I'm going to say, okay, before I start the program, I need to actually read in the stuff from the text file, from my test vector file. And so I'm going to use a function here called readmem. And then I can either put B or H or I think even O, but I wouldn't use O. B stands for binary, so you're reading it in a binary format. H stands for hex, so you're reading it in a hexadecimal format, which is to say we could, if we wanted to, do it like this and like that, where this is the hex digit 1 and this is the hex digit 1. But I'll leave it in binary, and I'll do readmem B. Now the thing you put inside this is the name of the file you're reading. So the file name is going to be testvectors.txt. And then the thing you put after that is what you're reading it into. So now I'm going to go ahead and write another line up here for internal logic signals. So I'm going to put test bench signals. And so I'm going to put a few things here. I'm going to put basically an array to hold all of my rows of my test vectors. So I'm just going to call it test vectors. And I'm going to make the bit width the same bit width as whatever my line is. So here I have 8 bits in my line. So my bit width for this is going to be 7:0. So I'm going to say logic 7:0. I'm going to call this test vectors. But it's not just a single line, even though that's what I have written here. It could be many, many, many lines. So you're going to make this an array of 8-bit rows. So you would specify that something like this. Say we had 100 entries, or in this case 101 entries. We would say, okay, we have 100:0 entries in our test vector file. And so what we're going to do is we're going to put this name here over here. And I think what I'll do is I'll name it something else so that you don't get confused between this and the name of the file. So I'll put that there. So I called this vect array, so my array of test vectors. And that's what I put here, and this is going to populate that array with the things I read in with my test vector file. This this bit width here, again, has to be the same bit width as whatever my rows are. And this value here just has to exceed however many rows I have. It doesn't have to be the same. It just does have to be more, though, if you want to actually read everything in. Okay, any questions so far? Okay, so another thing I'm going to do is I'm going to make a few other signals. And I'll just make them 32-bit wide. These aren't going to be like wires in my system. They're going to be like numbers in C++ code. So I'm going to call this one vect num and errors. So these are going to be numbers just in my simulation that are going to keep track of which row of my test vector I'm on and also how many errors I've seen. So what I'm going to do is I'm going to, in this initial block here, I'm going to set vect num equal to 0 initially and errors equal to 0 initially, just so that I know I'm starting the program with no errors and I'm starting reading from the very first index of my vector array. Okay, any questions for me? All right, so here's what we've done so far. We've created our test bench with some test bench signals to hold the test vector file, as well as to keep track of where we are on our test vector file, and also how many errors we've received. We've made our signals for the inputs and outputs of our device under test. We've instantiated the device under test. We have created signals for the clock and the reset for our system, and we've just now read in stuff into our vector array. So now here's the next thing we need to do. We need to actually feed in those values from the test vector array into the device under test. And so here's how we're going to do that. I'm going to have an always block, because remember, this always block executes whenever this occurs. And so what I'm going to do is I'm going to say, okay, every time I have a positive edge of the clock occur, right after that positive edge, I'm going to read in some values into my inputs. And so what would that would look like is right here, or sorry, that's the wrong clock edge. What that would look like would be something like this. Right here on this clock edge, that is when I read in the values. And so what I'm going to do is I'm going to write the next line. We have one block of delay after that first positive edge of the clock, and it's going to occur for every positive edge of the clock. And after that 1 picosecond delay, I'm going to read in the current row of vector A. So I'm going to say the following, and I want to read it in to a few things. I want to read it into D, that's the input that we're doing, and Q, the expected output. Now I'm going to put Q expected here, because this is going to be different from the Q we have in our device under test. This Q is the output of the actual module, whereas this Q down here is what we expect the module to output. So that's why I've named it Q expected, and that's why I'm going to put it as a logic signal here. And -1 to 0, and that would be Q expected. And so what I'm doing here is I'm going to say, okay, D and Q expected are going to read in the current row of vector A. So I'd specify that by saying vector A and then whatever my current index is, which is going to be vect num. So that corresponds to my current index. So again, all this is doing is it's saying, okay, I read in my test vector array up here, and I need to read in one row of it, just one row, into my D input and to what I expect Q to be as my output. So what I do is I say, okay, D concatenated with Q expected, because that's how I've written it over here, D followed by Q expected, is going to receive the value of whatever's in that row in my vector array. So on that first go, D would receive the value of 0001, and Q would receive the value of 0001. Okay, so I know I talked about that a little bit. Any questions about that?
How would it increment? Is there like a plus plus type
We're
of
gonna get to
operator?
that, yeah.
Oh,
Yep.
okay.
I don't know if there's a plus plus actually. I think there is. Typically though, you can just say vecnum equals vecnum plus 1. I don't know in Verilog. I don't think there's a plus plus. In System Verilog, I think there is. But in the test bench, you'll see in Dr. Harris's on Canvas that Dr. Harris has posted. I think it's just plus 1 instead of vecnum equals vecnum plus 1 instead of plus plus.
Oh,
Doesn't
okay.
really matter
Thank you.
though. Yep. So we'll do that after. So this block takes care of. Well, it's basically the stimulus for our device under test. That's kind of a technical term, but it's basically just saying these are the inputs, and these are your expected outputs. Okay, so let me comment this up a little bit. Device under test, generate my clock. Initialize stuff. Errors, test vector array. Okay, now here is what we've accomplished so far is we've made this a self-stimulating test bench. So it's able to read in from a test vector file and put it into my device under test, read those inputs into my device under test, and basically feed it different inputs over time. So we've made it self-stimulating. Now we need to make it self-checking. So that's the second part. And so what I'm going to do is the following. I'm going to say, take a look at, let's do it like this. So every time you receive a positive edge of the clock, the circuitry is going to receive the new inputs and then reevaluate itself and then become something else. So we need to check it sometime after that positive edge, sometime after we fed it those inputs. So what I'm going to do is I'm going to say, I'll check the values whenever we hit a negative edge of the clock. So here's what I'm going to write. Always at the negative edge of the clock. And again, this is so that the circuitry has time to actually do calculations for gates to swap values and stuff like that. So we apply things at the positive edge of the clock and we check them at the negative edge of the clock. And I'll put a begin here, and end. And I'll start this off by saying, well, if reset is on, I'm not going to do anything. Or in other words, if reset is not on, then I can actually do some checking. So here's what I'll do. Begin, end. So only if reset is off, i.e. we're not in this first part of my signal, only if reset is off are we actually going to do any testing. Are we going to check if the values are correct? So what that means is, despite the fact that we have a negative edge of the clock here, well, it says, okay, but reset is actually still on, so it's not going to go through that entire block. It's just going to exit it. And what we're going to do now is we're going to say, okay, well, reset's not on, say over here on this negative edge. So right here, we're going to say, okay, let's check to make sure stuff was correct. So here's what I'm going to do. If, and I'm going to check if my output that I got, Q, was the same as my expected output. You'll notice I put 3 equal signs there. That is on purpose. That's not a mistake. I'll explain why in just a minute. So if Q and Q expected are the same, then we're good. There was no error. But let's say there wasn't. There was a mismatch, that it was wrong. So Q is not equal to Q expected. What I would do here then is the following. And I would say, okay, I have an error. So what I'm going to do is I'm going to output to my terminal in ModelSim, and I'm going to say, okay, I received an error. So the way you do that is you say display, and then you put a string here. So we could say error input, and then I'll write this in binary. output binary, and then it's binary expected. Everywhere where you see that %b is just going to be filled in with a value that I'm putting over here to the right of my function call. And essentially what I'm going to do is I'm going to say, okay, this first b is going to be my input, so I'll call it d. That's my input. And then the second one is my output that I received, the actual output of the device under test. And then my third one is q expected. And so all this is doing is it's going to print out error input, and then whatever d is, comma, output, and then whatever q is, and then parentheses, and then whatever q expected is, expected. So that's just going to print that in a nice format to my terminal. Okay, so any questions on that? It's basically like doing a cout statement in C++. Or actually more accurately, like a printf statement in C. It's very similar to that.
And it would normally just go percentage O for like octal or percentage H for hexadecimal?
Yeah, so if I wanted to, I could put these all in hex, or I could put them in decimal with D. Yep, absolutely. Yep. Okay. The next thing I'm going to do is I'm going to take my errors, and I'm going to increment it, because I received an error, so I need to increment the number of errors. And what I'm going to do now is, if I'm outside of this, I'm going to say, okay, I just dealt with if there was an error. I'm going to now increment my count. So vect num equals vect num plus 1. And so again, what this is going to do is it's going to basically make it so I'm checking the next thing in my test vector up here. So that incrementing down there means that on my next go, when I have a positive edge of the clock, instead of checking the row I was on, I'm going to check the next row. So that's all that's doing. Okay. Now the last thing I'm going to do, and so now it's self-checking and self-testing. Now I'm going to put a little bit of code to make it stop itself when it's done. So I'm going to say if, I'll do it, yeah, test, no. So now what I'm going to do is I'm going to check if it's finished, which is to say that we've reached the end of the test vector file. So to know if you've reached the end of the test vector file, one way to do it is to check if the current row of your test vector array is empty or filled with nothing. So for example, here, let's say we had just this row populated. After we get to the second row, the test vector isn't going to read in anything. It's going to be filled with x's. And so what you'd put here is you'd say if vector a at my current index is equal to, and then I would say the test vector array has a bit width of 8. So I would say if it's the same as 8 bits of binary x, which is to say there's nothing populated in there, then I'm going to go ahead and end my my testing. So I'm going to say, okay, I'm going to display a few things that are important, that I care about. Display. So I'll output, for example, the number of tests run. So I'll say %d tests run with %d errors. And I'll put the first thing as the number of tests, which was vectnum. So that's how many tests we ran. That's how many rows there were in the test vector. And vectnum. And the second thing is just my errors. After that, I can halt or finish the simulation by saying stop. Okay, so let's take track of where we are, and then I'll answer questions if you guys have any. So we wanted to make a test bench. And so we did a few things. We made some signals for my test bench, which consist of the array for reading in all my test vectors, an index for which current row I'm on, as well as keeping track of how many errors I've received while testing, and an expected output for Q, which is going to be read in from my test vector array. I have some signals that are going into my device under test, like clock, reset, D, and Q, as well as the instantiation of that device under test here, with the appropriate parameterization and the port list here. I've made a clock signal for my entire system to run on. Not only my device under test, but also my test bench itself uses this clock. I've made some initialized values, so we start with the reset being pulsed on to 1 and then off afterwards. And we initialize our count of the index and the number of errors to 0. And we read in our test vector file into this array. After all that stuff is out of the way, we have 2 blocks here. One, which is the stimulus block, which basically provides an input to my device under test at every positive edge of the clock, and one for checking if there was any errors, which occurs at every negative edge of the clock. We check if the reset is off, then we actually check if there was a mismatch, and if there was a mismatch, we're going to display that there was a mismatch and increment the number of errors. And then after we do that checking, we increment our index, and we say, okay, well, if this next line is all X's, then that means that we've finished the testing, we've ran out of test vectors to test with. So we're going to output the kind of final sum or the final results of our simulation, which is we ran 10 tests with 2 errors, for example. And then we end our simulation. And this should not say end module. I don't know why that's there. Begin. Oh yeah, that should have said end. Okay, cool. So, now that I've kind of gone through how you do this, again, you can look at the example that Dr. Harris has posted in on Canvas. She has, I think, 3 test bench examples. Test bench 3 is the one that'll look like this one. It's the self-checking, self-stimulating test bench. 1 and 2 are also self-stimulating, but instead of a test vector file, you actually type it in directly in the system Verilog code, which is, well, you can do it. There's nothing wrong with it. But when you have really big, lots of inputs to check, lots of different possibilities to check, you typically don't do that. So if you look at test bench 3, that's the one that'll look like this one. Okay, so I went through a lot going through that test bench. Thank you guys for sticking with me. Did you have any questions in regards to them?
I have a quick question. Did you guys go over question 2 in the homework?
I don't think we did. We did not go over question 2. We went over 1 and 3, and yeah, we went over 1 and 3.
Okay.
Any other questions for me?
When we say it's a test vector, it's because it like has like rows of like tests, right?
Like why is it called test vector?
Yeah.
Yeah, it's just because every input you apply is a vector, which is like a row of information. Yep. Any other questions for me? Okay, well, thank you all for sticking with me. I know we're a little bit over on the office hours, but thank you for coming along and looking at how we do test benches. Let me think. I will still be here tomorrow for office hours for if you guys have any other questions, but I'll go ahead and end the office hours now.
Thank you so
Right.
much for doing that.
Thank you very much.
You're very welcome. All right, see you guys.